Welcome back, Organickers. This is John Hansen, and in this video we're going to be talking about interpretation and analysis of infrared spectra, something that you got quite a bit of experience in last semester, but that you'll also need to be able to use effectively this semester. Now, just a word about these video tutorials. In order for them to be the most effective, I want you to not just be passive watching them like you would a television or something, but be able to interact and work. And so you'll need a piece of paper and a pencil, and maybe one of your good friends will be the pause button on the video, so that if you need to stop and think about something, you can do that. That's the beauty of having a video like this. You can also go back and play something over. I also assume you're watching this on a computer, and you might want to have the Moodle page for the course open like we have on the screen right now, so that you can click on things and look at stuff as I describe it. So with that in mind, the first thing that I would suggest you do is scroll down on that first page and look where there's a link to Chem 251 IR examples. That's a page that's got a number of different IR spectra that we'll be discussing in this video. And I think the most effective thing would be for you to go ahead and pause the video and then print out those 4 pages, so that then you can annotate them as we go along. So I recommend you pause the video now and print that out, and then come back and start it up when you're ready. Okay, I've already got this on another page, so here's our Chem 251 IR examples page. And to get started, I'm just going to kind of review. I hope this is mostly review for you from last semester, but again, you might have gotten a little rusty over the break. So we'll start talking about some of the features of the IR spectrum that I expect you to be able to pick out and see. So the first thing is to divide the spectrum up into different spectral regions. And if we look along the axis here, you remember that most modern infrared spectra are recorded in wave number, which is kind of that odd unit which is 1 over the wavelength. And in the case of IR spectra, they're in reciprocal centimeters, which you can't quite read here. So the typical spectra run from about 4,000 reciprocal centimeters down to something like 400, 500 reciprocal centimeters for most organic chemists. This is the normal IR region. The peaks, remember, go down because we're looking at percent transmittance here. So if there's nothing being absorbed, you have essentially 100% transmittance, and then as you absorb, your peak goes down. So I guess it's actually a valley, but we call it a peak. To start off our analysis, let me remind you of some of the main areas of the spectral window. So one of the first, if I start from sort of left to right, if we start in the region from about 3600, which is around here, to 2700, down at around here, and up, that region right around there is a region that's characterized by vibrations of a heavy atom, that is a non-hydrogen atom, to a hydrogen atom. So like a carbon-hydrogen bond, an oxygen-hydrogen bond, a nitrogen-hydrogen bond. All those bonds tend to vibrate and give rise to absorptions in this region. The next region that we tend to emphasize comes from about, I would say 2300 to 2100. So that'll be right down around here, over to about there. That region right there would be characterized as the triple bond region. So carbon-carbon triple bonds and carbon-nitrogen triple bonds would be the major things that we would see in that region for organic chemistry. And finally, the last really region that we're going to spend a lot of time analyzing comes from about, I would say, 1850 down to 1500, or a little bit below. So this region right around here. And that's going to correspond to your double bond region, like carbon-carbon double bonds and carbon-oxygen double bonds specifically. You could also have carbon-nitrogen double bonds in that region. And so each of these 3 regions will be areas where we'll be able to look to characterize the various functional groups that we normally encounter. Now that leaves a large area of the spectra that we're not analyzing at all, that area from about all the way down to the end here, around 400 or so, up to about 1500. That region we commonly call the fingerprint region. for reasons that will become apparent later. We could match up to spectra in that region to see if they were identical, and that would give us strong confirmation that that was the correct compound. A lot of the vibrations in that region are complex. They may be bending vibrations. They can be some carbon-carbon single bond or carbon-oxygen single bond vibrations, and occasionally we can characterize a few of those. But in general, because there are so many different types of vibration that come down in that region, for example, in this spectra, you can see there's a lot more peaks here than there are up in these regions, it becomes fairly difficult to do detailed analysis. There will often be multiple peaks contributing to a single area, and so it'd be hard to tell exactly what's going on. So most of our discussion today will be focused on these first three areas, and that's where I would like you to focus your attention. I'll also note that all the vibrations that we'll be normally talking about in these three regions are stretching vibrations. So along the bond axis, the two atoms are moving apart and then closer together each other in a vibrational motion. That can occur down here also, as I mentioned, for carbon-carbon or carbon-oxygen single bonds, etc. But it also will often be due to vibrations that are due to bending vibrations rather than stretching vibrations, and so you'll have a lot of those that occur down in this area. But these three regions up here will be looking exclusively at stretching vibrations. Okay, now you might say, okay, well, you've started telling me about these different regions. Where could I go to get more detailed information, things that maybe we don't cover in this tutorial, etc. And so I'm going to go back to our Moodle page and just point out a couple resources that I've made available for you. This first one that I'd like you to look at is the one down here called Introduction to Interpretation of IR Spectra. So I'm going to click on that and bring up that page. For those of you that had me last semester, we had this as a handout, and I'll be also providing one the first day of class this semester when we're talking about IR spectra. This is my attempt to sort of condense into, sort of as small a possible region as I can the information I'd like you to know. And it's organized by the spectral region. So for example, when I said that 3600 to 2700 was the XH region, the bond vibration between a carbon hydrogen or an oxygen hydrogen or a nitrogen hydrogen, that was coming from this handout, for example. And then furthermore, we've broken it out into even more detailed subcategories for different things that come in there. And so, for example, the alcohol OHs or the amine NHs and alkyne CHs come up in a higher region, 3300 to 3600, whereas a regular CH from an alkyl group might come at around just slightly below 3000. So you can see how this is brought out, sort of pointed out here. And then I've got a few even more detailed notes here of things to look for. So that's our XH region. I mentioned the triple bond region down here, 2300 to 2100. There's really only two functional groups that we normally encounter in organic in that region. Although I might mention that CO2, which is in the air, of course, if it doesn't get subtracted out, will occasionally come near that region. Finally, the C double bond X region, which you'll see here a lot of carbonyl, C double bond O are in that region, and then the C double bond Cs. But again, we can break them out into different subregions. And finally, the fingerprint region down from 1500 all the way down. There's also a few notes at the end about some other characteristics to keep in mind when interpreting IR spectra. For example, that the wave number is related to the force constant K, which in our case is normally the bond strength, and to the masses of the two atoms on the ends of the bonds typically. Also, I'll point out also the intensity of an absorption is usually related to a change in dipole. So a C double bond O vibration will have a much stronger intensity because of the dipole there and the change in dipole that occurs as it stretches versus a C double bond C, in which case there's not usually as large a dipole, so those peaks will be smaller. So with that in mind, I'll let you look at that sometime at your leisure, but that's where a lot of the information that I'll be talking about today comes from. Now there's a related handout that I'm not going to give you, but is available to you online I mean, I'm not going to print it out for you. And that is the same information, but now arranged by functional group rather than by where they come in the spectra. So for example, if you wanted to know, oh, what should I look for an alcohol? I will say, oh, an OH stretch will come in this region, 3200 to 3600. The CO stretch will come down around 1050 to 1150. So it's sort of a different way of organizing it by functional group, which is essentially what we're going to want to be doing as we analyze these spectra, is try to characterize which functional groups are in the molecule. Okay, so let's go back now to our IR examples, and I'm going to go ahead and delete these sort of regions. We'll kind of, by the way, notice there's really nothing in the region in this spectra, so that means we don't have a triple bond in this molecule. And of course, I've got the structure shown below, so it's sort of pretty obvious. So let's start off. We're going to start off with this carboxylic acid and just see how we go about interpreting this spectra. So first thing I want to point out is if we start up in this upper region where we said there's XH bonds, we can see that there's sort of two different types of bonds or vibrations that we're kind of seeing here. We're seeing some sharper ones right here, and then there's sort of a very broad bond here, or absorption here. This broad one is due to the OH, this OH stretch. Let me just try to kind of put a little circle around that so I can sort of show it here if I can do this. You know, something around that region, this big broad OH. So if we wanted to label that, and you know, I'll be asking you to do this on exams or quizzes, for example, to label the different absorptions, we could go down and we could say, okay, this is the OH stretch, and you know, I'll just put a little arrow on that, maybe pointing to that region right there. Okay, so I'm identifying that as an OH stretch. This sharp peaks down here are actually due to the CHs. So we have lots of CHs here, and there's lots of CH stretches. CHs don't have as strong a dipole change as an OH, so in general they're weaker, but we have an awful lot of them, so we see them coming out at the bottom. They're also much sharper. We often see that molecules that can hydrogen bond, like OHs, or I mean parts of molecules like OHs or NHs, have broader peaks. This actually also occurs in the NMR spectra, and it's due to the wide sort of variety of OHs that you have depending on the type of hydrogen bonding that's going on. So some molecules are more hydrogen bond than others in sort of the mixture of all the molecules in there. And so you get kind of this broad dispersion of various types of stretching. So that's our OH. I will point out that in a carboxylic acid, this OH is often so broad, it's often, you know, sometimes it's hard to even know whether it's really a peak or whether it's just like kind of a cruddy looking IR or something. So that's can sometimes be a challenge. Of course, if you have a carboxylic acid or suspect that you have one, you're going to know that you have a carbonyl in it, and that's going to come down in this region with our C double bond C, and so I'll put a little box around this. Oops, so I've got to select my box here. So that peak right there is our carbonyl. Notice that it's the strongest peak in the spectrum, and that's very common for carbonyls. That strong change in dipole that occurs means that the carbonyl stretches are often the strongest absorptions in the IR. Now, you can label that the way we labeled it here. You can see a C double bond O stretch. That's great. But I want to sort of point out in a little more careful analysis where exactly this is coming. Now, to do that, let's look at this axis again. So this is 500, 1,000, 1,500, 2,000, and then this is 3,000. And if you look at these little tick marks, you'll notice that the scale kind of changes here, so that, you know, this is 1,500 to 2,000, and that's 2,000 to 3,000. So in a lot of the spectra that we'll be looking, we'll see that sort of change in the scale, so you want to look carefully at them. In your book, the scale is continuous throughout. That is, it's the same distance between 1,000 and 2,000 as between 2,000 and 3,000. So that's a little bit something different in these two spectra. So sometimes you need to get the exact wave number or something a little closer. So if we go here, this is 1,500, that's 1,600, and that's 1,700 right there where my cursor is. So you can see that this carbonyl is just slightly above 1,700. That's a very common place to find a carbonyl. Carboxylic acids, esters, aldehyde, ketones all absorb almost exactly that same place. I would say 1,700 to 1,750 reciprocal centimeters is about where those come. And again, just to kind of show you on our little chart that we were looking at a minute ago of infrared interpretation, if we go down to that region of the carbonyls, you'll see that I have listed here 1,700 to 1,750 reciprocal centimeters, aldehydes, ketones, esters, and acids. Okay? Now you'll notice that there are some things that are carbonyls that fall sort of outside that range. We have a few that come higher. That could be an anhydride, which is a functional group we'll be talking about some in a little bit this semester. It actually has two absorptions. You'll see when we look at the anhydride functional group, there are two carbonyls. Acid chlorides, which we'll also be talking about, also often come up in this region around 1800. But another kind of unusual thing is that the ring size, if we're in a ring, can also influence the carbonyl frequency. And I've got listed here a 6-membered ring cyclohexanone is 1715, which is sort of our normal number. Then as the ring size contracts to cyclopentanone, a 5-membered ring, and cyclobutanone, a 4-membered ring, the wave number goes up. So those are some things that come slightly above 1750. And then if we would look slightly below 1700, we have sort of conjugated carbonyls or amide carbonyls coming slightly below. So we kind of have these three separate subsections that we can look at. And we'll see some examples of those in a minute. Okay, so we've done a pretty good job of characterizing the absorptions. Let me kind of finish this off as the way I would like you to do it if you were doing this for a quiz or an exam, is to characterize these different regions. So I'm going to put down here, okay, we've got our C double bond O stretch. And so maybe I'll put a little arrow there, saying, okay, it's going to that peak right there. I seem to lost this guy. There we go. Okay. And then this region right here, do you remember what we said this was? These sharp guys coming out? Yeah, that's the CH stretch. And you see those in almost all organic molecules, so it's not really too exciting to note them, but we can do that. Put a little arrow pointing out those guys. Okay, so we've done a nice job of annotating the major peaks in that spectrum. We're not going to normally be annotating the peaks down in the fingerprint region. We won't always know. You'll always sort of see some right around the 1400 to up to maybe almost 1500 range, something like this. Those are some CH bending that you often see. Now, when I point out the CH stretch, I'm going to do a little something here to kind of be a little more careful about it. Notice that these are coming just slightly below 3000. Those ones that are slightly below 3000 are your typical, and I will say sp3 CHs. So maybe I'll be even more specific here, and I'll label these as sp3. I don't really know how to do a superscript here, so I'm just going to leave it that way. So we'll call those sp3 CHs there. And I'd like you to kind of be that definite or that specific when you're identifying those. Okay, so that's the typical way we're going to characterize it. I'm not going to go in this much detail and drawing all these things out, but you should be doing this on your page as we go through this tutorial and identifying the various stretches and bends or anything that we need to look at. Okay, let's go to the next example. The next example, I've given us another carbonyl compound, but this is an aldehyde in this case. Okay, so since we have a carbonyl, we know we're going to be looking for that carbonyl stretch, and there it is, big as life. You can see the tail of this guy and this one here, they're almost identical. you couldn't really tell whether it's an acid versus an aldehyde just by looking at the carbonyl stretch. They come in very similar places. But of course, we already know that with an acid we had the OH, and we identified that over here. What do we see for a carbonyl of an aldehyde is we see a very distinctive CH stretch that comes a little bit below the normal sp3 CHs. So I'm going to go ahead and put a couple arrows here to point to these two that I want to point out. There's one right there, and there's another one right there. Okay? They come at about 2750 and 2850 reciprocal centimeters or so. Those are the CH stretches for the carbonyl of an aldehyde. So they're the CH that's on the carbonyl. If you have a ketone, of course you don't have a hydrogen here, you have another carbon, and so those peaks are typically not visible. Sometimes it can be a little tricky to tell whether that one at 2750 is really just a normal CH or whether it's part of an aldehyde. But that one at 2750, see we're right down here about 2750, that one is far enough out that you wouldn't normally see one. So if we look at the one above, you see that there's a little bit kind of because of the OH there, but there's not really a nice 2750. And this peak that I've highlighted right here with my cursor is corresponding closely to that peak right there, and then we have another one on the shoulder here. So you usually can pick out an aldehyde by seeing that there's a carbonyl and then looking here for that doublet. Again, the one of them can sometimes be a little bit close, but a peak at 2750 is pretty distinctive for that. What about other carbonyls? Let's scroll down. What do we have on the next one? We have a carbonyl, and here what I'm trying to highlight is the fact that this carbonyl is conjugated. So remember, conjugation means that we have an sp2 center next to our, in this case, multiple bond, our carbonyl, and so we get some overlap there. That leads to a shift, a slight shift in the carbonyl frequency, and now if we look really closely here, you'll see that this peak comes just slightly below 1700. So notice that that peak right there, that little tick mark is 1700, and this is slightly below. So what you might want to do is annotate this, get a little arrow and put it on there, and I'm just going to draw a little arrow there. Okay, and say something like less than 1700 implies that we have a conjugation. So that is sometimes distinctive. If you're looking really closely, that's a good clue that your carbonyl might be conjugated. This is a regular ketone. If this aromatic ring wasn't here, that ketone would be slightly above 1700. Now, when we're looking at aromatic compounds, we have some other stretches that start to become distinctive. All the first two spectra we looked at were just alkyl groups, and so I want to point out the new ones. Now, these peaks right here, can you help me out and tell me what these are? I'm just going to kind of put a little box around them. Those guys right there. I'll kind of move it down to the axis so you can sort of see where they are. Okay, those guys are our CH stretches, but are sp3 CHs again. Notice, however, that there are some little peaks that are above 3000. Those are actually the sp2 CHs. I haven't shown them here in this line drawing, but there's a carbon with a hydrogen there, carbon with a hydrogen there, carbon with a hydrogen there, etc. And those CHs are coming slightly above 3000. So if we were going to annotate this, we might put that this is an sp2 CH stretch. And I'll put an arrow just to point to exactly where I mean, right there. Okay, and there's a couple different ones. There's a couple different CHs here. So those guys are slightly above 3000. So what you're starting to learn is some kind of important numbers to keep in mind. 3000 right here, if we're slightly below that, those are normal CHs. If we're slightly above that, then that's going to be sp2, and in a minute we'll see sp-CHs are even higher. Another important number then again is this 1700. Slightly above 1700 usually suggests that we have a normal carbonyl. Slightly below it will suggest as either conjugation or, as we'll see in a minute, an amide. And again, if it's a lot above 1700, for example, closer up to 1800, it might mean a small ring, for example. We'll see an example of that. A couple other things I want to point out that you can look for that are very distinctive for the aromatic ring are, of course, all these C double bond Cs in the ring. Now, of course, if we drew a resonance form, there would be C double bond Cs in the alternating position, so maybe you could say they're C 1.5s or something as opposed to doubles. But those come down in our carbon-carbon double bond region as a series of multiple peaks, usually 3 or 4, with usually the first one being very close to 1600. So this peak that I'm highlighting right here, that is one of our C8 carbon-carbon stretches of the aromatic ring. Here's another one slightly below it, and here's another one down around 1450. So I'm going to go ahead and put a little box around that. You might want to do the same on your sheet. So let's kind of just do it this way. I'm going to go right from about there to there. That region in there is our normal aromatic region. And again, I want to emphasize that usually there's one right around 1600, and then there are multiple other ones, 3 or 4, and they'll come in slightly different places depending on the aromatic ring and the substitution, but usually that's very distinctive. Now we'll see in a minute that our carbon-carbon double bonds come slightly above that, more in the range of about 1650 plus or minus some. Not as far down as 1600. So it's usually, you're usually able to tell the difference between a regular alkene carbon-carbon double bond and the aromatic carbon-carbon double bonds. Also, of course, with an alkene, you would typically only have one. You wouldn't have multiple ones. There's a couple other things to mention about the aromatic, although I'm not going to have you identify it normally. Typically, you'll have some aromatic CH vibrations down here, and they're usually fairly intense around, you know, this 700 region, something in there, 700 to 900, something like that. Again, normally it's hard to tell because you have a lot of things coming down in this fingerprint region. Obviously, you can see a lot of peaks here. In fact, I read one book where they talked about, you know, it's almost easy to tell if you have an aromatic versus not aromatic IR by just looking at your fingerprint and seeing if you have a lot of peaks. Now, I don't think I would go that far, but it is, there are a number of different vibrations that come from the aromatic ring. But there's one other thing that if you see is very kind of characteristic for aromatics, and that's this region right here. Notice that it's above our normal sort of 1700, and these peaks are fairly small. But you'll see these kind of little bumps. These are referred to as overtone bands, just the way you can have an overtone in a musical instrument note or something like that. They're coming from some of the vibrations down here. And you'll see multiple small humps like that, and that's very characteristic for an aromatic compound. So if you see that, that really is a good clue. Let's just look at some of the non-aromatic up here. Notice we don't have kind of a series of those bumps right up here that we had for that aromatic. And same thing here, there's no bumps up in that region. So if you start looking for those, you'll sometimes see them. Now, you know, there are some cases where they're hard to see. It's hard to tell whether it's just noise up there or something. But, you know, it's a good clue. You can certainly identify it, but you want to corroborate it with these sorts of vibrations that you're seeing in the sort of 1600 to 1450 range, and then maybe some sp2ch stretches up above 3000. These are sometimes very weak also, which can be a little bit misleading sometimes. So, you know, sometimes you'll just see a little blip on the side and it won't be quite as distinctive as this one. Okay, let's move on to page 2 now. And I'm showing an amide because I wanted to show you another example of a carbonyl which is below 1700. So here is our 1700 where I put the cursor right here. And again, you can see that we have a very strong carbonyl stretch. But now this is almost down to, you know, maybe 1650, 1660 or something. That's actually getting down to where sort of normal carbon-carbon double bonds come. But a very, very strong absorption and characteristic of an amide. Now, if we have an amide, we have a nitrogen. That nitrogen wouldn't necessarily have to have a hydrogen on it. It could have 2 other alkyl groups, but oftentimes they do. And those NHs then will come up in the region where we expect nitrogen-hydrogen bonds to come, which is up in this region up here. And in fact, you can see 2 peaks right here. I'm going to draw a little box around them, which is very characteristic for an NH2. And this could be true either for an amide NH2 or for an amine NH2. So we see two peaks. They're typically up significantly above that 3,000 dividing mark. So for the sp2CHs, that was going up maybe as far as 3,100, where I've moved the cursor here. Anything that's up higher than that is not going to be an sp2CH. We could have an NH. We'll also see we could have OHs in this region, although usually you wouldn't have a double one, and the OHs are a little broader. NHs are a little sharper. OHs are oftentimes a little stronger also, although would be hard to tell that in a spectrum like this. One other thing that can come in this region that we'll see in a minute is a an SPCH bond. So we'll see a copy of example of that in a minute. But the combination of the strong carbonyl that's down below 1700 significantly and some NH stretches. If this was an NH with another R group here, so only one hydrogen, then we typically only have one of these peaks rather than two. So that's a characteristic of the amides. Now, we do have some other peaks in this molecule, so I just want to point them out. So we've got these peaks right here. What are those, do you think? Give you a hint. Here's 3,000. Where are they? Slightly below 3,000. So yeah, so those peaks right there are your typical sp3CHs. So you might want to label those sp3CHs because you can see we have some of those in this spectrum. Again, everything down here is just fingerprint region. These are probably some of the CH bends right here. Finally, I think the last carbonyl compound that I have to show you in this set of examples is a cyclobutanone. And remember, we just mentioned those briefly when I was looking at the handout. When you put a carbonyl in a ring, and it wouldn't have to be a ketone, you could have an oxygen here, so it would be a cyclic ester, and we'll be talking about those sorts of functional groups in this semester in class, that when you put them in a smaller ring, it causes the shift of the stretch to come to higher frequencies. So again, my cursor is sitting right on 1700 now, and you can see that this peak is actually slightly below 1800, not slightly below 1700 or slightly above 1700. And so that's kind of out of the range of normal thing, or the normal stretch would maybe come up as far as 1750. So again, this is giving us some clue that there's something special here that we might be able to interpret, and in this case, it's the fact that it's in a ring. A three-membered ring would come even higher. Five-membered ring would come down maybe more right here, and a four-membered ring down a little bit further. So if you see a carbonyl and it's unusually high, that is usually giving you a clue that there might be some information there. As I mentioned before, it could also potentially be an acid chloride, although that functional group we won't run into a lot. They're fairly reactive compounds, and so we won't be seeing a lot of IR spectra of those, but if you did, you would see something up there. And the anhydrides can also come this high, but then again, usually then you have two different peaks instead of one. Just one other thing that I'd like you to characterize if you're doing this is right here. What are those guys again? Yep, our sp3CHs. So again, we have sp3CHs not shown on this line drawing, and we're seeing their vibrations right there. Finally, at the bottom of page 2 on this handout, I've got two spectra that I kind of squished on here together, and they both are alkynes with a carbon-carbon triple bond. And there's a couple things I want to illustrate here. The first one is the carbon-carbon triple bond and the carbon-nitrogen triple bond, remember, come in a very distinctive region around 2300 to 2100. So there you go, that guy's just slightly above 2100, sort of a wasteland. We don't normally have things in that region. There it is. That's our C triple bond C stretch. So if I wanted to make a little quickie annotation here, I could just kind of do something like, whoop, there it is, C triple bond C stretch. Okay. This is what we call a terminal alkyne because it's on the end of this chain, and so it has a CH attached to the end. That CH then is an sp carbon with a hydrogen, and that comes even higher than the sp2 CHs, which remember came slightly above 3,000. So if I kind of go back to my 3,000 point here, everything slightly below that is the sp3 CHs, which we have a lot of here. If we had an sp2 CH, it would be sort of in this range of 3,000 to 3,100. But if we have an sp CH, it comes up, wow, way up here. Oops. I want my arrow key there. I'll do it this way. At about 3,300. So again, if you were going to label this for me for a quiz or something like that, I'd like you to put something like, you know, SPCH stretch. Okay, and so there we go. Okay. And you could also label these as sp3CH stretches here. So that's very distinctive for a terminal alkyne. So I wanted to show you what an internal alkyne looks like. So that's the next one. That is where the alkyne is in the middle of the chain rather than at the end. Now in that case you don't have a CH on the alkyne because there's carbon-carbon bonds on either side. So we don't see this SPCH. So you can have an alkyne and not see that. That's pretty obvious if there's no terminal CH there. But you'll also notice that this triple bond vibration, which was occurring, you know, around 2100 to 2200, something in there, that it's gone, or at least it's very small. So let me go ahead and get my little rectangle cursor here. I'm going to circle that guy right there. Well, you know, if I was looking at that and I didn't know what was going on with this spectra, I didn't know, for example, that it was an alkyne, I might say, well, I don't know, maybe it's just some little peak and overtone band or something. I don't really know. And I don't really have a lot of good things to go on. Now, why is it so small in the spectrum? The reason, again, goes back to why are peaks, what makes a peak more intense or less intense in the IR. And what was that? It was the change in dipole moment. So when we have the terminal alkyne, the CH end has different electronegativity, if you will, or different amount of electron density than the left side. So we get a fairly decent change in the dipole when that vibrates. But when it's internal, it's more symmetrical. And so a symmetrical alkyne actually, if it was perfectly symmetrical, would show no peak at all because there would be no change in dipole. Now, it's a little bit different having this, you know, 3 carbons on this side versus 1 carbon on that side. But it's similar enough that there's not much of a change in a dipole. Even with a triple bond on the end, there's often not that change in the dipole, so these are not like super strong absorptions. So you have to be a little bit careful with symmetrical molecules. You don't see the C triple bond C stretch. That's also true for carbon-carbon double bonds. So if I had a perfectly symmetrical alkene, it wouldn't show any carbon-carbon double bond stretch either because of the fact that there would be no change in dipole. Of course, that's sort of, I guess, a relatively unusual case to have a completely symmetrical molecule like that. And I'm not going to try to fool you with that on an exam, give you an example of one that doesn't have anything to see and expect you to know that. But you might run into it in real life. You're going to be doing unknowns. You could have something where it's a weak absorption, and so you need to understand that that could happen. For a nitrile, a C triple bond end, of course, you're always going to have a dipole, so those always showed up nicely, usually with an intensity sort of similar to the one up here that you're seeing for this carbon-carbon triple bond. I haven't shown you an example of that, but you might want to go and look up some nitriles, and we'll talk about how to go look for some spectra of things in a minute. Okay, let's go down to the next page, page 3, and I'm going to transition and talk a little bit more about analysis, but also some of artifacts that we might see or things about looking at the fingerprint region. So let's start off with this alkene with an alcohol in the molecule. So now we have 2 functional groups in this molecule, and essentially they'll act fairly independently. We'll see both of those functional groups appear in the IR spectrum. So let's start, we'll kind of look at the biggest peak. This is very characteristic for the OH, right down around 3,300 to 3,400, a very broad, often the most intense peak because, again, the OH has a large change in dipole when it vibrates. That's very characteristic of an alcohol. And after you've seen a few of them, and most of you, I think, are already proficient enough to pick out those OHs quite quickly when you see them. So an alcohol OH. We'll see in a minute a phenol OH may look similar to that, but certainly an alcohol OH is very characteristic there. Here's our 3000 mark, so slightly below that. What did we say? Yep, sp3CHs. Now I'm going to put a little box around this guy right here. That's our sp2CH. So we've got CHs here, here, and here off of our alkene. Remember, we also saw slightly above 3000, 3000 to 3100 were our aromatic CHs. So they also come in this region. So you might say, oh, well, I've got an sp2CH. I don't know whether that's an alkene or an aromatic yet, but I can try to go figure that out. If we thought it was an aromatic, we'd look down here, and remember what I said, there'd be multiple peaks, usually one at around 1600, and then maybe one next to it, or a couple others down as low as 1450. You know, it's hard to say there. But if I go up here, I see there's a peak right there, but in fact that peak is significantly above 1600, and it's essentially just a single peak, it looks like, by itself, which is characteristic of an alkene. So I'll go ahead and put a box around that. You should go ahead and label that as our alkene C double bond C stretch. So, oops, I didn't get that picked right. All right, so label that C double bond C. Maybe I'll do one more for you just to make sure you're in the right place here. C double bond C stretch. There it is. Maybe I'll even put a little arrow to it. Okay, so there's our C double bond C stretch. Notice that it's less intense by a lot than the carbonyl, because again, we're not having as large a change in dipole, but it's a fairly significant peak, and we can see it. Usually they come right around 1650. So somewhere between 1650, maybe as low as 1630, up as high as 1670, 1680, you know, depending on the exact situation. But, you know, right around 1650, usually see a single peak, and then confirming the sp2CH. I've shown you a very similar molecule down below. You can just see that I've essentially just like moved this methyl group over there. So we'd expect in the IR this to have a very similar IR pattern. So sure enough, there's the OH, essentially is indistinguishable from that one. There's our CH stretches right there. Here's our CH sp3CHs. And finally, when we look at the alkene, there's the alkene in that molecule, and there's the alkene in that molecule, virtually indistinguishable in terms of where they came. This brings up an interesting point. Usually when we analyze an IR spectrum, we can't tell exactly what the molecule is. We can just say, oh, it has these functional groups, and maybe if we have a list of possibilities, we can pick out which one it is, but we can't give the exact structure. However, if, let's say, you're doing an unknown and you want to know exactly what it is, then what you can do is, if you have some spectra that you can look up and match, you can look at the fingerprint region and see if the fingerprint regions are similar. So let's just kind of take a quick look at these two fingerprint regions. You can see the fingerprint region in the lower spectrum down here is quite different than the fingerprint region here. I mean, look, we have this big absorption right here, and that doesn't look like there's anything really big there. And, you know, the patterns down here are quite different. I mean, so, you know, just quick visual inspection shows you that these two are very different. And if you had, let's say, an unknown, and you went and you looked up that IR and compared it to your unknown, you should be able to tell the difference by just looking at that fingerprint region. So what we're looking at is sort of where peaks come and their intensities, relative intensities to each other. And you should then be able to do it. Of course, you know, you'd have to have already narrowed it down to something with, let's say, this molecular formula and be looking through various possibilities and sort of comparing their IRs, so it could still be a little bit laborious. But of course, that's what we're going to be learning shortly, is other spectroscopic techniques like NMR, for example, which would help us to narrow down maybe even quicker a few possibilities that we could then look up the IR spectra of. The last spectra here on page 3 lets me illustrate a slightly different point. This is a carbonyl of an aldehyde. And we talked about that earlier. Do you remember what we looked for those guys? Let's sort of kind of go up and remind you up here. Right there was oh, I'm sorry, the second one we looked at. Here's our carbonyl of an aldehyde. Remember I had those arrows pointing? Do you remember what those were? Yep, that was that distinctive CH stretch. And we had two at 2750 and 2850. So I'll go down, and sure enough, there's our carbonyl, remember, slightly above 1700. There's one of the CHs right around 2750. And there's the other one right there on the shoulder, almost hard to pick out, right? But that guy's very distinctive, so that's pretty confirming. But that's not really what I wanted to show you or emphasize here. What I wanted to emphasize was this funny peak right here. What does that look like? Look up here. What do we see here? What was that peak? Remember, that was our OH stretch. This looks like it's coming around the OH or maybe an NH stretch or something like this. This can be very confusing. It's like, what's going on there? In this case, it's an artifact, but it's one that you often see with aldehydes. At the end of last semester, we talked about something, if you had aldehydes and water together, that they could make a hydrate, where you had two OHs off of this carbon instead of the carbonyl, and that in fact at equilibrium you had about a 50-50 mixture of that in water. Now, this isn't in water, but there's water in the air, and your aldehyde could be contaminated with a little bit of that diol or the hydrate of the aldehyde, and so that would show an OH here. So this is a common sort of thing that you'll see in some aldehydes. Now, in the one that we had above, I won't go scroll back up to it, but you can look, it didn't really show a very big peak there. But, you know, if your aldehyde isn't really clean, or if it was a humid day or something, you might pick up sort of a peak in that area. There's also sometimes peaks in this area if, for example, you're using a sampling technique. We used to use salt plates a lot, which could absorb water from the air. And water also has absorptions in this region. So little peaks in this area, students would often try to assign to things, but they were really just due to water on the salt plates. So little peaks here can sometimes be deceptive. Notice how much stronger a real OH is than that guy. But you know, just to kind of put that out there. On the next page, I'm going to look at some phenols. And in fact, I'm going to look at 3 spectra, so this is page 4 now, of exactly the same compound, but they've been taken under different conditions. And although you know, this isn't something that I'm going to dwell on a lot, you need to know about it because when you go to look up spectra, they may be acquired in different ways. So I'm going to show you 3 different spectra of this 4-ethyl phenol. Well, let's do a little quick analysis just to kind of get up our practice. You guys might know enough to sort of do this, so why don't you pause the video and try to, you know, assign all these, and then you can come and see what I say. Okay, so I assume you're back and you've analyzed this. Were you able to find the OH peak? I'll go ahead and circle it. Hopefully you did. It's right up here, right there, that big broad peak. It'll often look almost just like an OH for an alcohol. This one looks a little funkier, but it's definitely in that region around 3,300. What about these guys here? Did you characterize those as your normal CHs right there? And then look at this little guy. That's the one that's above 3,000. That's our sp2 CHs. So hopefully you got that guy picked out. Again, with aromatics, sometimes they're a little tricky to see. And those are just our normal sp3 CHs due to the ethyl group there. What about the aromatic? What do we normally look for there? It's those C double bond C vibrations. And remember I said there's usually multiple ones at slightly above, starting at 1600 and going down to maybe 1450 or something. So these guys right in here are probably definitely our carbon-carbon double bond ring guys. So again, there's one at around 1600, one slightly below this one. This has also probably got some of the CH bends in it, so I'm not sure if that's just CH bends or whether it also has one of the vibrations from the ring in there. But very characteristic of the aromatic, that pattern, so that really kind of locks it in for us. Now, you'll notice that this is labeled as a KBR disk. So oftentimes solids are acquired by grinding them up with KBR, and KBR doesn't absorb in the IR, so you can grind it up and make a little disk out of it and send the IR light through it, and you'll get a spectra that'll look something like this. Another technique for doing solids is something called new-Joule mole. And the reason why I'm going to point this out is because you can see that there's something different about the new-Joule mole. Notice that here's our OH, that looks pretty similar, but the CH region looks quite a bit different. And the reason for that is that new-Joule is actually a mineral oil, which is an alkane type compound, so it's got a lot of CHs from the new-Joule itself. So that new-Joule peak right there is the CHs, and the increase in intensity in this peak right here, which is the one right there, is due to the new-Joule CH bendings. So when you do a new-Joule, you have to sort of ignore this peak, and it would obscure any others, any CHs from your compound, and there will be extra peak like right here in your spectrum too, which will be due to the new-Joule. So again, this is a common way to prepare a sample, and so if you're looking up on a website and they say it was in a new-Joule mole, you have to know to sort of kind of ignore those guys. Finally, one last way, and there are other ways, is to dissolve your compound in carbon tetrachloride, which also doesn't have too many absorptions in the IR. You'll notice that in this spectra, they sort of, this region right here, there's like a little gap there, and then over here there's a gap. That's because they've omitted those regions because you have strong absorptions from the carbon tetrachloride itself. So they don't want you to get fooled by that. There's a couple other interesting things. Is if I compare this to the peak up above, like the spectrum here, first of all, look at that OH. That OH has changed a lot. Instead of being this big broad thing, it's coming considerably higher, up around 3600 now. Let me go ahead and put a little arrow on that. Right there. That's our OH stretch. It's a lot sharper because now if it's in a dilute solution, it's not actually hydrogen bonding with other molecules because they're too far apart, whereas in, of course, the solid, they would be hydrogen bonding. And so it causes them to shift up and to get a lot sharper. So that's kind of an unusual thing. Now, for our class, I'm not going to be giving you any solutions. We don't normally do solution cells in the lab either. So again, I just wanted to point this out because when you go to look up a spectra and compare it, they maybe have taken it in carbon tetrachloride solution, and if you're comparing it to it, you say, well, that doesn't look anything like mine. Even though, okay, well, here there are some aromatic, etc. So you have to be comparing spectra that come from similar sort of techniques. Now, in our case, our new IR spectrometer that we're using now uses an ATR attachment, attenuated total reflectance, has a diamond anvil that we're squeezing it on, so we're not actually using any of these techniques. The best one to use for comparison purposes is probably the KBR Disk method. That's probably the most similar to ours. I will just say that the ATR tends to de-emphasize, that is, make the peaks up in this region, let's say above 2000, be less intense than normal. So if we took the spectra of this compound on our instrument, I'd expect these peaks to be less intense than they are here. They would still show up, but they'd be less intense. So when you're comparing there, you have to be aware of that. Most of the databases that are available now don't have actual ATR data on them. They were acquired usually with a KBR disk. Now when I say most of the databases that we look at, what databases am I talking about? Well, let's go back to our Moodle page here. And I want to show you right up here, I put it under our some useful links because we'll be using this for more than just IR, we'll be using it for NMR and mass spec, etc. Is this NIMC spectral database. Now I think many of you probably used this last semester, but let's go ahead and click on it and take a look at it. This is a Japanese database and it's free to use and it's just a great resource for us because it has thousands of compounds and lots of different spectra of them. So I'm going to agree to the disclaimer. It's also nice of them to provide an English language page. And what you can do is you can search by compound name, molecular formula, and all other sorts of things like whether it has a IR peak in a certain place or whether it has certain numbers of atoms, etc. So in our particular case, I just want to show you, let's say we were going to look at that 4-ethylphenol, or let's just say we wanted to look at well, yeah, let's go ahead and put that, 4-ethylphenol. We'll hit return, it'll do a search, and return these compounds. So I think maybe I typed the name in. No. So these are tert-butyl 4-phenylphenol, so they're slightly different. Here are the different spectra that are being acquired: mass spec, carbon NMR, proton NMR, IR. We won't talk about Raman or ESR in this class. If there's yes, that means they have a spectra, and if you click on it, you'll go to that spectra. So this is a slightly different compound. This is the tert-butyl ethylphenol. And notice up in the top here, they tell us that this was a liquid film. So if you have a liquid and you just put it on a salt plate as a thin film, you'll get this. And that'll be also very similar to the spectra that we would expect in our ATR spectrometer. So here it is. Here's those carbon-carbon double bonds for the aromatic ring. Here's our OH, and here's our normal CHs showing up there. If you go over to the left here, you'll notice that you could look at other spectra, the proton NMR spectra, which we'll be talking about on, I guess, Wednesday mostly. So, oops. Scroll down, you can see the proton NMR spectra. We'll be learning about carbon NMR spectra. You can see that. And you could also look at the mass spectra. So just be careful that if you get a compound from the database that you're looking, that you know what type of IR is and it's in the correct format. I will also mention that another way that sometimes you'll see IR peaks or IR spectra being acquired is in the gas phase, and those are quite different from the ones in the liquid phase. I mean, not super duper different, but different enough that it's a little tricky. So I would avoid those because we don't normally do that in organic. We usually use condensed phase spectra. Okay, so this NIMC database is one that I think you should get used to using and use quite a bit. If you don't know the name of something, the best thing to do, of course, is, but you know what the structure is that you're looking for, the best thing is to go for the molecular formula. So if I wanted to put in the molecular formula for my 4-ethylphenol, it's got 6, 7, 8 carbons, so I'm going to go C8, and then it's going to have H, it's going to have 4 on the aromatic ring, it's going to have 1 on the OH, so that's 5, and then from our ethyl group we have another 5, so that's going to be H10, and then we're going to have our oxygen atom. So I'm doing this on the fly, I haven't pre-scripted this, so I hope I got this right. Let's search for that. Oh, return to search page, that didn't work too well. Let's see what I did here. Oh, C8HH. That's not going to work. So C8H10O. So you put carbon first, then hydrogen, and then the others in alphabetical order. So let's see if I can do this correctly this time. Ah, now we've got lots of compounds. And so there are a lot of compounds with that molecular formula that we could possibly be looking at. And so again, we would want to look through. Here's why I didn't find it when I was typing 4-ethylphenol, as they're using the name p-ethylphenol. We'll be talking about this nomenclature when we talk about aromatics, but that means that the two groups are in the 1 and the 4 position. So this is, in fact, is the 4-ethylphenol, and I'm going to click on this category right here, which you can't tell now, but is the IR one. Let's go look at the IR spectra. So these are the IR spectra that I had on the handout that you were looking at, and I just like to illustrate this one because notice that in the database they actually have 4 different spectra. They have the new Joule mole one, the carbon tetrachloride, the KBR disk one. Those are the 3 we looked at. They also have a liquid film one, which means it must be low melting enough that they were able to heat it up and just melt it onto the plate. That actually looks pretty close to the KBR disk one also, and would look probably similar to the one from our ATR attachment on our spectrometer. The reason why I wanted to sort of show you this site, in addition to just showing you some of these spectra, is to tell you that this is a great way to look up things if you're not sure what a particular functional group looks like. So for example, let's say you're saying, well, gosh, John mentioned nitriles, but I wonder, what some nitriles look like. You can search in the compound name, and as long as it says match partial, it'll find anything that has nitrile in the name. So I'll hit return, and I say, oh, acetonitrile. Okay, that's a nice simple nitrile. Let's see what its IR looks like. So I'll click on it. I'll look up here. I can see it's thin film, so that's a good one for us to look at. And wow, Look at that big C triple bond N guy there. Okay, so I say, wow, okay, that's interesting. There's 2 peaks. I wonder if that's common. Well, let's go back and look at maybe a different nitrile, just maybe a little bigger one. Well, here's propionitrile. Now, you might not know the structure. You know it has a nitrile, so let's click on it. In the spectral database, they often show you the picture down here, although this one doesn't have it. But again, look at that C triple bond N, as big as life. You can really see that. So by looking at a few of these, you can start to see, oh, you know, now I'm kind of used to seeing what those nitriles look like. So when I see one, I won't be too surprised. So this is also a great way to make problems for members of your study group. You can just look up some different spectra and print them out, and then, you know, cut off the parts that, you know, describe what it is and say, okay, what can you tell me about this? So it's just a great resource for getting practice at looking at spectra. And of course, it's a great resource when you're doing your unknown to sort of compare your unknown to various things. Okay, well, I think that's about all I wanted to show you in this video. One thing that I will mention is to go back to our home page here, and one place that you might go to practice is this organic chemistry online page. If you click on that, you'll see that there's a lot of problem sets that you can do. So infrared spectra problems you can work on by clicking on that, and we've got lots of problems that you can begin to work on. So it's a great little resource. I will note that they've put the wavelength in microns at the bottom and the wave number in reciprocal centimeters at the top. So that's a little different from what we've been looking at. So you can look at this spectrum, and hopefully based on what we've discussed, you'll be able to say, oh, well, let's see, where is that peak? 15, 16, 1700. What comes at 1700? Yeah, okay, I'm going to leave it for you. Oh, here's a peak slightly below 3000. What's that? So you can start to get an idea of what's there, and they give you a molecular formula so that you can use that to try to figure out what the compound is. And then they have some analysis, interpretation, and structure, which you can click on. I'll leave that for you to do on your own. Okay, well, that's about it for now. I'm looking forward to seeing you in class, and in class we'll work on these IR practice and these quiz 8 ones, so you don't need to start on those. We'll do those in class, first day of class. Take care, and see you in class.